Hey everyone. Today we're going to start on our Chapter 9 experience. And Chapter 9 is when things start to get really interesting in stats. I feel like I say that every chapter, but in Chapter 9 we start having the opportunity to answer some, real questions and real hypotheses that we could have. And answer those questions based on the numbers that we're getting back from our surveys and experiments. So this is where we actually analyze in even more direct way than we did with confidence intervals. We're going to analyze the data that we produce from all of our experiments and surveys. So let's get started. A local engineering firm had to conduct a series of layoffs recently, and they're going to lay off 10 people. The company has 180 employees that could be laid off, and all are equally qualified. So the company decides to use a lottery system to carried out by the manager to decide who will be laid off. Now, the manager posts a list of employees to be laid off. 5 of the employees are women and 5 employees are men. That sounds pretty good. One woman claims that this is gender discrimination and starts a lawsuit. Whoa! Why is she saying gender discrimination? Half of the people laid off are men, and half of the people who are laid off are women. What additional information are we supposed to need to actually evaluate is this gender discrimination? So let me take this with the extreme example with what if there were only 5 women in the company and all of them were laid off? That seems a little rich now, doesn't it? All 5 women happen to be laid off. So I think what's clearly important here, or the additional information needed, is, well, how many women were in the company? What was the gender makeup of this, engineering firm? Once you have that down, then, I guess we'll need to answer that question if we want to go further here. So let's say, I don't know if this is for sure, but we're going to assume that there were 120 males and 60 females. So it seems as though proportionally more females were laid off than they should have been. So question 2 says, how can you investigate this gender discrimination claim? And let's detail a process that can be used. We want to use a process that is, probabilistic in nature. We want the probabilities to be similar to 120 males to 60 females, which is, I think, 2 males for every female. One of the first thoughts here would be to use dice, where you have 1 through 2 is female, and then 3 through 6 would be male. And one problem with the dice thing is that we're going to assume independence here. But, in reality, as soon as we fire a male, then the probability of firing another male would be changed. On the other hand, we're only firing 10 out of 180, which is less than 10%. So the 10% rule makes this kind of independent. Another way that you might want to do this is maybe with a spinner or a random number generator. Well, the spinner and the random number generator with only 3 outcomes, that will run across the same problems above. And the last way that we'll investigate here is with a random number generator, but with 180 outcomes, where outcomes 1 through 60 are female and 61 through 80 are male. And using a simulation with this kind of random number generator, then you don't have to assume anything about independence, because the probabilities are preserved, because it is a 1-to-1 assignment between employees and random digits. So over here it says we're supposed to complete our investigation below, and you probably guessed it, I'm going to pick option 3 with a random number generator. And this gives me an opportunity to use my Google Sheet that has a simulation. Okay, so you can see here that we're back on my simulation page. This time we're doing a sample and we're counting how many are between 1 and 60 in this first 10. So I'm going to start by going ahead and randomizing that range. And let's see, how many are between 0 and 60 in our first 10? We've got 3, 30, that's 1, 25 is 2, 17 is 3, 14 is 4, number 9 is 143, and number 10 is 67. So that should be 4 successes for a sample proportion of 0.4. That is correct. And we'll just go ahead and keep track of it over here. So we're going to do a few of these. Here you see I've already done 11, and we can already see how the dot plot is shaping up over here. It looks like we're getting a peak over at 0.3, and it does look kind of single peaked really and symmetric. So we're not going to know more until, or we need to confirm our suspicion. So we're going to do a few more of these samples. Okay, well, we just did 50 samples, and these are the proportion of females that were laid off from each of those samples. And I haven't looked at the dot plot yet, so let's see what that looks like. Okay, here's our dot plot, and it looks like we were getting a peak over here at 0.3, that is, and then, you know, a little bit on the right skew, but not really a lot of right skew. So I think I'm going to stop here, and we'll put this dot plot in our worksheet. Okay, I've changed the title here to be proportion of women laid off of the company. I thought that would be a little better. So what percentage of the dots represent half or more of the females being laid off? Now we're saying half or more because we're concerned that there was discrimination. And if there's discrimination, that means the number that we got, 5 out of 10, 50%, or something greater than that would have happened in our simulation. So that's why half or more, 0.5 or more. And let's count those dots. And I counted 12 out of 50, or 24%. Let's interpret that in context. So the first thing that had to have happened is we conducted an impartial lottery. Okay, so we conducted a fair lottery. And that's what we're assuming to start this off. We're assuming that the company did a fair lottery. Okay, so assuming this was fair and every employee had the same probability of being laid off, there is this 24% probability now. And it's a 24% probability that 5 or more females would have been laid off from the company. Which brings us to, does this give us convincing evidence for gender discrimination? Now, remember what we said. Things get suspicious. Things get kind of... things get very suspect if that number is less than 5%. That would mean that if the lottery was fair and a less than 5% probability occurred, or an event that only had a 5% or less probability of occurring did occur, then we would say, well, that's fishy. Something happened there. Either our assumption of a fair lottery was off, or we just happened to get a freak set of samples, or a freak sample. Considering we have a 24% probability, I don't think that's very rare. So if the lottery was conducted fairly, then laying off 5 or more women wouldn't be a rare occurrence. So if it's not a rare occurrence, then we couldn't say for sure that this was gender discrimination. And that right there is kind of Chapter 9 in a nutshell. This is everything we're going to be doing, maybe not with simulation, although, you know, there is a lot to be said about doing these kinds of problems with simulation. But the kind of logic that we employed here is going to be the same thing that we do for the rest of the chapter. So let's take a look at our important ideas. The first thing we have is the idea of a hypothesis. Now, when we do significance tests, which is what Chapter 9 is about, when we do a significance test, then we have to have a pair of hypotheses for this to work. The first one we call the null hypothesis. Now, the null hypothesis takes the form of, you would write down H naught, colon, and then mu is equal to a value, or P is equal to a value. And what the null hypothesis does is it gives us a value that we suppose mu or P is equal to. Oftentimes, this is the number that we're trying to disprove. So if we're trying to show that, the mean is not 14, then we have to go in with a null hypothesis that mu is 14. So it is a number that we're trying to disprove. And we're going to contrast that, or we're going to couple that with the alternative hypothesis, HA. HA is the thing that we're trying to prove true. So this comes in 3 different varieties, and of course it could be either for a mu or a p. I've only written 3 things here. The first one I wrote down is mu is greater than the value, or mu is less than the value. Then I also wrote p is not equal to a value. So it's a combination of mu or p and p, one or the other, and then greater than, less than, and not equal to, one of those 3, and then the value. Incidentally, the value that you see in the alternative hypothesis is the same value that you're going to see in the alternative hypothesis. Oftentimes that value is called the null value, so we'll just call it the null value, and that'll probably help us out. So the same null value appears in the null hypothesis and the alternative hypothesis. Now the next learning target we have here is the p-value. And p-value sounds kind of exotic, but it's really not. We've already met the p-value in all actuality. And the p-value is the probability of getting experimental or survey results or more extreme than those survey results purely by chance if the null hypothesis were true. So I'll show you where we saw the p-value. Over here, our survey result was actually how many people were fired, was 0.5. And here we calculated that the probability of getting 5 or more females, or 0.5 females or more laid off, was 24%. So this 24% right here, this was actually a p-value. Finally, we have the learning target of the conclusion. And the conclusion is always we either do or we do not have convincing evidence against the null hypothesis. So how do we know if we have convincing evidence? There's this thing called the significance level, and it is given the variable alpha. For most of our experiments, we're going to use alpha is 5% or 0.05. And alpha gives us our measuring stick about whether or not we reject the null hypothesis. If the p-value is less than alpha, then we say that the results are statistically significant. We talked about that already. And if they're statistically significant, that means we have evidence against the null hypothesis. And if we have evidence against the null hypothesis, we reject the null hypothesis. So when we do our experiments, what we're hoping for is that we get a p-value that's less than alpha, because that means that we can reject the null hypothesis and conclude that the alternative hypothesis must be true. Let's take it to check your understanding now. And calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average, and is that true? So state a hypothesis for performing a significance test, and make sure we defined the parameter of interest. So we have to, we're going to be doing this symbolically with the symbol mu. So we're going to have to say what mu is. We start off by saying that mu is the mean calcium intake of teenagers, because that's what we're really trying to figure out. And then we say that mu is 1300. And we get 1300 here because that's the number that we're measuring up against. We're saying the NIH calcium intake is 1300. So we're going to start by assuming that the calcium intake for teenagers actually is 1300. And if we do things right, I don't know if right's correct there, but if we do all of our experimenting, then hopefully we're going to show that mu is less than 1300. So that's how that number works. We start off by assuming that the thing that we want to prove is not true. It's kind of like you have to have the burden of proof. You can't start by assuming that teenagers aren't getting enough calcium. You've got to assume that teenagers are getting enough calcium. And how much calcium? Well, right at that borderline, 1300. So we're going to start by assuming that teenagers get enough calcium, get 1300 milligrams, and we're off to prove that the amount of calcium is actually less than 1300. If we know we want to prove that the calcium intake is less than 1300, then that's going to tell us that our null hypothesis is mu is equal to 1300. The null hypothesis is always equal to a number. Parameter equals a number. Let's take a look at number 2. Researchers decide to perform a test of using hypothesis stated in number 1. They ask a sample of 20 teens to record their food and drink consumption for one day, and the researchers then computed the calcium intake for each student, and the data revealed that the sample mean, X bar, is equal to 1,198 milligrams, with a standard deviation of 411 milligrams. Researchers performed a significance test and found a p-value of 0.1404. So what would it mean for the null hypothesis to be true in this setting? Well, it's pretty clear. Since we know what mu is and we know that is equal to 1300, then we just have to put those two number sentences together. So if the null hypothesis were true, that means that the teenagers are getting an average of 1300 milligrams of calcium a day. Now for number 3, it says to interpret the p-value. And luckily for us, let's talk about what it is before we go to the lucky part. So the p-value assumes that the null hypothesis is true. So we're assuming that teenagers get 1300 milligrams of calcium a day. And if that's true, that means that the probability of getting a sample that has a 1,198 milligrams average or less, that's the extreme part, that number or less is 1404. Now that's kind of a lot to reason out, and we kind of get lucky because there is a sentence frame for this one as well. So we have, if the H naught in context is true, there is a p-value probability of a sample of size, whatever our sample size was, having a parameter greater than, less than, or as extreme as our statistical value. Let's copy and paste that over. And we'll just start putting our text in here. So if H naught in context, what is H naught in context? Well, that would be the average daily calcium intake of teenagers at 1300 is true. Then there is a p-value. What is our p-value? That's 1404. So there is a 14.04 probability of a sample of size 20 having a parameter. Now our parameter was the average intake of, here it is, the mean daily calcium intake of teenagers. So we're going to put that in there for parameter. So having a mean daily calcium intake of teenagers as, let's see, less than, I think is the one that we want. And then our value was 1198. Like always, we're going to read this one more time for readability. So if the average daily intake of teenagers is 1,300 milligrams is true, I don't think I need the is true part here. There is a 14.04% probability that a sample of size 20 has a mean daily calcium intake of teenagers. Okay, I think the of teenagers is redundant there. As less than 1198. Okay, I don't think I need as also. Reading one more time, if the average daily calcium intake of teenagers is 1,300 milligrams, then there is a 14.04% probability of a sample of 20 has a... No, that doesn't read well as well. So there is a 14.04% probability that a sample of 20 has a mean calcium intake less than 1198. Okay, so that sounds pretty good. Let's go ahead and move ourselves on. What did we conclude at the 5% level? Well, I think our p-value is bigger than 5%. So we cannot say that the null hypothesis is incorrect. Now there is a sentence frame for a conclusion here, and we're going to copy and paste that. Okay, so we got a p-value that was greater than alpha. And then read the next part carefully. The data does not support the alternative hypothesis. So when you write your conclusions, you're always writing your conclusions in terms of the alternative hypothesis and not in terms of the null hypothesis. Because you're kind of, you want to prove that the alternative hypothesis is true. So we're going to write this in terms of the alternative hypothesis. And if the data doesn't, if we can't reject the null hypothesis, then the data doesn't support the alternative hypothesis. The data actually supports the null hypothesis. It never supports more than one of the hypotheses. So the data does not support that the mean calcium intake of teenagers is less than 1,300. So let's read that for readability and make adjustments. Since the p-value is greater than alpha, the data does not support that the mean calcium intake of teenagers is less than 1,300 milligrams. Sounds pretty good to me. Okay, this kind of concludes what we are working on for today. This is just a start for our journey into significance tests. I think you're going to be relieved that we have those sentence frames for you to work off of, and I do encourage you to use them. We do things a little bit differently than you probably see in a lot of other sources. The one that kind of strikes me is that I always want you to write your conclusions in terms of the alternative hypothesis, and that's not always the way what you're going to see out there. So keep that in mind as you move forward and look at other sources. And I'll see you next time when we look at the remainder of this section.